Good afternoon or good evening, everyone. I'm not sure when you are listening, watching this video. Hopefully it's still Wednesday and you are staying on track with your schoolwork. I know you should have some math work and some English work in addition to your chemistry work and whatever other teachers are able to communicate with you at this time. Hope you're using this week before spring break also just to get used to this process, because it looks like we may be continuing to do some online learning even after spring break. That decision hasn't been made yet, but that is a possibility, so it's good for you to be prepared. So far, a lot of you have turned in your work from Friday night's homework. You have uploaded it on the class assignment, or those of you who are able to get it in on time, you emailed it to me. If you emailed it in after Monday or during Monday, I believe I replied to your email saying to go ahead and post it on the Teams under the Assignments tab. I created an assignment for those Friday night notes. It's much easier to submit on Teams than to submit via email, and it's easier to keep track. Both you have a record and I have a record that you have it done, and it marks what time it was turned in. So Teams is turning out to be a very useful tool. As you can see in today's video, we have our DNA on the same screen. So I'm going to continue to do that. Go ahead and put the DNA in there, and you'll copy it down as normal in class. You're going to go ahead and put the date on your paper, the topic, the EQ, copy the DNA, the learning targets, and the homework. As usual, draw a line underneath, and then you'll need to pause the video and go actually do the DNA. So you're going to go write the balanced equation for the formation of water. You're going to interpret the equation in terms of moles, particles, and mass. Now, if you don't know what that means, it's because you missed yesterday's lecture. So I would stop this video now and go do yesterday's lecture first, or you'll start to be lost if you do these videos out of order. So make sure you've got yesterday's notes, take them out, go ahead and look at them, and do today's DNA. Remember, the last statement in the interpretation is to show the law of conservation of mass, that mass is neither created nor destroyed during a chemical reaction. It is conserved. All right, go ahead and pause the video now. Finish copying down the DNA box, answer the DNA, and come back when you have your answer. I'm going to pause for a little bit while you do that. Okay, I'm back with you, and I know that most of you need more than 30 seconds to get all of that done. So I hope that you have paused the video to finish that. If you haven't, pause it now, because I'm about to go over to the DNA answer. And you learn best when you've tried it yourself before looking at the answer. Be sure you're done before you keep going. All right, here we go. So the balanced equation for the formation of water from its elements. Water is made from hydrogen and oxygen. And if you remembered, hydrogen is diatomic. Oxygen is also diatomic. You cannot have a balanced equation unless you remember that they both come in packages of 2. And in order to balance, you needed to have 2 hydrogens reacting with 1 oxygen. Remember the invisible 1 that's here? We don't write it, but we understand that there is a 1, coefficient of 1 on the oxygen, will produce 2 waters. So if you got that right on your notes, you can do our ever famous cha-ching and let me know, hey, Miss Aguilar, I got this one right. Next, you were to interpret. So remember, our first interpretation is in terms of moles. So let's go ahead and show you what that should look like on your paper. You should have 2 moles of hydrogen reacting with 1 mole of oxygen to produce 2 moles of water. So that first interpretation should be super easy because you'll notice every one of them use the same thing: moles, moles, and moles. The second interpretation is our interpretation of particles. This is the one where you have to do a little refreshing. Remember, there are 4 types of particles: atoms, ions, molecules, formula units. Each one of these starts with a nonmetal. Hydrogen is a nonmetal, oxygen is a nonmetal, and this water starts with hydrogen. It's also a nonmetal. That means all of these are molecules. So we're going to interpret them in terms of molecules. It should look like this. You should have 2 molecules. Remember, if you're going to abbreviate, you can stop at the C, but nothing shorter than that, of hydrogen react with 1 molecule of oxygen and 2 molecules of water. You're more than welcome to abbreviate each of these as long as you stop at the C. Our third interpretation was the mass. So you should have taken a minute and added up all of the different parts of these molecules. If you haven't done that, you should pause the video before you go ahead and look at the answer. So your answer should have been the total mass of 2 hydrogen molecules. That means you're taking the mass of hydrogen, multiplying it by 2, and then multiplying that by 2. Well, for oxygen, you're taking the molar mass of oxygen from the periodic table, multiplying it by 2. For water, you're taking the molar mass of water and multiplying it by 2. Once you've done that, go ahead and watch for the answer. If you haven't, click pause, figure it out, and then check your answer. So you should have come up with 4.04 grams of water, 32.00. Don't forget the 00. It's not optional. All molar masses must have 2 decimal places, and 36.04 grams of water. Hopefully, you took the time, did that right, and you got a cha-ching right there. The last thing is the law of conservation of mass. Remember, the law of conservation of mass tells us that the total mass of the reactants must equal the total mass of the products. So we have to add up the total mass of the reactants, and in this case, there is only 1 mass for the products. So 4.04 plus 32.00 gives us 36.04 grams of the reactants equals, we're using that for our equals, 36.04 grams of products. And if you did all of that right, well done, ladies and gentlemen. You get a big check mark for your efforts today. The last thing you're asked to do is to write the mole ratios for this equation. So if you haven't written the mole ratios, again, just go ahead and pause the video and write the mole ratios. You should have written 6. If you don't know what mole ratios are, look at your notes from yesterday's lecture. All right, let's go ahead and take a look at the mole ratios. So we're going to have a mole ratio of hydrogen to oxygen. Let's do that one first. You can see that there are 2 moles of hydrogen reacting with 1 mole of oxygen. The mole ratios would look like this. Right? They're going to come from this equation. So our first set of mole ratios is right here. 2 moles of hydrogen react with 1 mole of oxygen. And those come right from that relationship. 2 moles of hydrogen and 1 mole of oxygen. And then we write the reciprocal. So simply flip that over. 1 mole of oxygen reacts with 2 moles of hydrogen. All right, now you've seen the first example. You should have on your paper already 4 more mole ratios. If you don't, pause, write them out, and come back and see us. Let's do our second one. Our second mole ratio, we're going to go ahead and continue with the oxygen and look at how it reacts with the water. 1 mole of oxygen produces 2 moles of water. And then again, the reciprocal of that, 2 moles of water, comes from, I should say, 1 mole of oxygen. And our last mole ratio would be the two things we haven't related yet, which is 2 moles of hydrogen produce 2 moles of water. So we'll go ahead and set that up. 2 moles of hydrogen produce 2 moles of water, and then the reciprocal, you're going to go ahead and flip that over. 2 moles of water are made from 2 moles of hydrogen. And that's it. 6 different variations of mole ratios from this equation. Hopefully you did it well and you've got to change. If you didn't, go ahead, stop the video at any time, rewind. This is the beauty of online education. You can stop me, go back and replay what I already said, and hopefully that will help clarify any questions. All right, let's go on to our notes for today. Draw a line under your DNA and we will move on. So today we are still on 12.2 and we are looking at mole to mole conversions. How do we use these mole ratios to make a conversion? I just want to stop right here and make a side comment. You know, I'm posting these videos on YouTube, and the beauty of that is I can go really slow and you can go ahead and play it back at 1.25 speed or 1.5 speed or 2 speed, depending on how comfortable you are with the material. You don't have to listen as slowly as I'm going. And if I go too fast for you, you can also play it back at 0.75, so it slows down the way that I'm explaining it. So even though the video may be 25 minutes, for you it could take 12 minutes if this is really easy for you. Or if it's challenging, you could play it slower and you could play it for 35 minutes. So there's a lot of freedom. I know that YouTube doesn't play on your laptops, so hopefully you're grabbing a cell phone or using your computer at home to watch them. All right, let's continue here. So the mole ratio is going to be the conversion factor that we are using. Remember, a conversion factor takes us from one unit to another unit. And as we saw in our DNA, the mole ratios come from the coefficients. Every balanced equation must have coefficients. So these two steps, first we're going to find our known and our unknown, as usual, and then we're going to set up a mole ratio. The work that we're doing today is a one-step conversion, simply takes us from moles of A to moles of B. If you look at your stoichiometry chart, that mole ratio is the red bridge. Look at the moles of A box to the moles of B. There's a bridge there. I guess on your paper it's black and white, not red. But that is what we're looking at. The mole ratio takes us from A to B. So here's our first problem. Remember, you don't have to copy the problem. And we have an equation, though, that's been given to us here, and it's already balanced. So you can just write it out. I believe this is the equation we used in our notes yesterday. It shows us that one molecule of nitrogen reacts with 3 molecules. Let me show you where I'm reading here. So one molecule of nitrogen reacts with 3 molecules of hydrogen to produce 2 molecules of ammonia. Or in terms of moles, 1 mole of nitrogen reacts with 3 moles of ammonia to produce, oh, that was incorrect. That was 3 moles of hydrogen to produce 2 moles of ammonia. So there's our equation. Hopefully you've written that down now. Now take a minute and look at the problem and write down your known and your unknown. All right, I'm going to go ahead and show you the known and unknown. If you haven't finished writing them down, just pause the video. When you're ready, hit play again. Don't let me move too fast for you. Okay, here's the known. Our known is that we have 7 moles of nitrogen. You can see that right here. Let me highlight it for you. 7 moles of nitrogen. It says that it's reacting with an excess of hydrogen. Now that's something that might be new for us. Excess of hydrogen. What does that mean? That means more than enough. The hydrogen's not going to run out, so we don't have to worry about the hydrogen. It's not even part of our known or unknown. They're just telling us, hey, you got plenty of hydrogen. So hydrogen is not a concern. What's a concern are the fact that we only have 7 moles of ammonia. That's our concern. So our unknown then is what they're asking here. How many moles of ammonia can be made? So we actually 7 moles of nitrogen, and how many moles of ammonia can be made? So let's take a look. This is our unknown. Our unknown is moles of ammonia. Now you'll notice something. I usually just put known and unknown, but now I've added something a little bit different, right? I've put A and B because this is what happens in stoichiometry. In stoichiometry, you go from A to B. You go from one chemical to a different chemical. That's what's unique about stoichiometry. That's why we have to cross that mole ratio bridge, because we are changing from chemical A to chemical B. If you start and end with the same chemical, you are not doing stoichiometry. Stoichiometry requires a change from one chemical to another. So in this case, we are starting with nitrogen, but we're being asked not about nitrogen, we're being asked about ammonia. So it is a one-step conversion. We'll set up our known 7 moles of nitrogen times our conversion factor. Now our conversion factor, where does that come from? It comes from our mole ratio. So let's take a look at our mole ratio here. We're going to first take a look at what we have. We have moles of nitrogen. So if I go over here, I know there's a visible 1 in front of my nitrogen. So that's what I'm going to put on the bottom, because remember, I want it to cancel out. So that is 1 mole of nitrogen. So I'm going to go ahead and put that in. 1 mole of nitrogen. And what goes on the top is going to be my unknown. I want moles of ammonia. Well, then I go to the equation and I look. How many moles of ammonia does that 1 mole of nitrogen make? It makes 2 moles. Mole ratio, 2 moles of ammonia. So that is what goes up here on the top, because that's my unknown. 2 moles of ammonia. Now notice these numbers come from the coefficients. That's why they're called a mole ratio. They come from the balanced equation. Without a balanced equation, you cannot do stoichiometry. Well, you don't need a calculator for this one. It's a very simple problem. It's all set up for us. All right, let me get rid of all of this excess, and we can go ahead and solve the problem. Simply, right, 7 times 2. And we all know that's 14, but we also know that moles of nitrogen are going to cancel with moles of nitrogen. And we end up with 14 moles of ammonia. A very simple first stoichiometry problem. We're going to go on and do 2 more problems today, and that'll be our lecture for today. If you need to pause and retake a look or replay any of that, go ahead and do that now. If you're ready to move on, let's go ahead and go to the next slide. All right, so let's continue our practice. You've already written down step 1 and step 2. You've already written down the balanced equation for the formation of ammonia. I've got 2 problems for you to practice. Here's your first one. I'd like you to pause the video now and go ahead and write down your known and unknown and solve the problem, then come back when you're done. Okay, Let's see how you did. Let's first identify our known and our unknown. It says how many moles of hydrogen are required to completely react with 8 moles of nitrogen. So we've got 8 moles of nitrogen. That's what we know. So that's what you should have selected as your known. Our unknown is moles of hydrogen because it says how many moles of hydrogen. So you should have selected moles of hydrogen as your unknown. Now remember, it's asking us about producing ammonia, but that doesn't mean ammonia is a known or an unknown. They're just telling us this is what's going to be made. But what we're really interested in is the hydrogen and the nitrogen. So if you need to solve the problem now, go ahead and pause the video. If you've already solved the problem, let's check out your work. First thing you do is remember it's stoichiometry, and in stoichiometry we always start with one chemical and with a different chemical, which is why we've started with nitrogen and we're ending with hydrogen. If we don't start with one chemical and end with another chemical, it's not stoichiometry, it's molar conversions. Nitrogen is becoming hydrogen, and this is our relationship. This is how nitrogen relates to hydrogen. It is an invisible 1 and a 3. That's what you're going to use to solve our equation. So here's our known, 8 moles of nitrogen. We're going to set up our conversion factor. And then we want to look to our equation. That's why we have it. We're going to look to our equation and we're going to find the nitrogen and ask ourselves, how many nitrogen are in this equation? Ah, there's only 1. So on the bottom, I'm going to write that out, 1 mole of nitrogen. And then my unknown is what's going to go at the top, up here. My unknown is hydrogen. So I go take a look at the equation and say, oh, I have 3 moles of hydrogen in the equation. So that's what goes on the top, 3 moles of hydrogen. After I've done that, my moles of nitrogen will cancel out. And I have another simple math problem here. I just take the 8, multiply it by the 3. 8 times 3 is 24. We get 24 moles of hydrogen. If you did well on your notes, I'd love to see a big check mark right there showing cha-ching, I got this, Miss Aguilar. If you're confused, pause the video, rewind it, watch it again before we go on to our last problem, because I only got one example left, so take advantage of each example. I'm going to go ahead and put question number 3 up. Once you read it, pause the video and write your known and unknown and solve. Come back when you're all done and I will set up my answer, and hopefully you've got this and you're ready to jump into your homework. All right, welcome back for our last problem. Let's go ahead and read the question carefully. How many moles of hydrogen are needed to react with an excess of nitrogen to make 10 moles of ammonia? Now again, I want to call your attention to this excess. Means more than enough. So we've got more than enough nitrogen. We don't need to worry about the nitrogen. It is not part of our known or our unknown. What we do know is that we are starting with 10 moles of ammonia. So that is our known, 10 moles of ammonia right here. That's what we know. What we want to know is moles of hydrogen. How many moles of hydrogen? So that should have been your unknown, moles of hydrogen. Again, we know it's a stoichiometry problem because we are going from A to B. We are going from one chemical, in this case ammonia, to a different chemical, hydrogen. That means we're about to do a stoichiometry problem. So we're going to put our known down on our paper, 10 moles of ammonia. We're going to set up our conversion factor, and we're going to find ammonia in our balanced equation. Let me do some erasing up here. So I've got a lot of work from our last problem, and I don't want that to be confusing. So just give me a minute to get this all cleared out here, and then we will get back. All right, here we go. We're going to look up ammonia in our equation. Our equation tells us there are 2 moles of ammonia. So that's going to go on the bottom, 2 moles of ammonia. It's not a molar mass. It's the mole ratio from the balanced equation. Our unknown is hydrogen. So we're going to go ahead and look up hydrogen on our equation. There are 3 hydrogens. So on the top, I've got 3 moles of hydrogen. It's a mole ratio. 3 moles of hydrogen. Then our moles of ammonia cancel out. And again, we've got a pretty simple math problem. Shouldn't need a calculator for it. What's happening here is we've got 10 times 3. 10 times 3 is 30. We're going to take that 30 and we're going to divide it by 2 because we always divide by what's on the bottom. So 30 divided by 2 is 15, and we end up with 15 moles of hydrogen. So hopefully that went really well for you today. And again, remember, if it didn't, just replay the video. It's almost better than school because you can go as slow or as fast as you want by increasing the speed. All right, ladies and gentlemen, so let's go ahead and end this here. You've got homework where you're practicing these, and you're practicing some of the things we learned yesterday, which is writing the mole ratios and interpreting the equation that we practiced during our DNA. Have a great rest of the day. Stay safe. Don't touch your face. Wash your hands. And make sure you're helping your parents out around the house. All right, I'll see you on Microsoft Teams.